In this video, we're going to take a look at the nature of covalent bonding. Covalent bonding usually involves the octet rule and how nonmetals come together to complete their octets. When we form covalent bonds, again, we have nonmetals which are really close to being a noble gas as far as their electron configuration is concerned, so no one wants to give up electrons, so the two atoms, or three or four, whichever it takes, to make that molecule come together to share electrons to then get to a complete octet, to be like a noble gas. We don't possess the electrons like we do in an ionic compound, so the ones that are shared actually kind of count double. So each person within that bond is counting the 2 or 4 or 6 electrons that are within the bonds between those atoms as their own possessive electrons. That gives them then a total of 8. We see this with a single covalent bond when looking at a hydrogen molecule. Again, hydrogen with one valence electron, wanting to get to 2 valence electrons to be like helium, ends up sharing one pair of electrons between those two hydrogen atoms, each giving them the feeling of having those 2 electrons like helium does, completing their first ring of electrons. Again, held together by those electrons between those 2 nuclei. Sharing that one pair of electrons is called a single covalent bond. When we do that, we show that they're sharing those electrons by putting those 2 dots right between the 2 hydrogens, again indicating that they are sharing those 2 between them. And then when we get to what's called a structural formula, the dot of those 2 electrons are being shared actually are replaced with a dash. So the structural formula is better than just using the formula itself because it shows which atoms are actually next to which other atoms, how they're sharing their electrons, and the way in which they are arranged. And H2O, it tells you that's made up of 2 hydrogens and 1 oxygen, but when looking at H2O's structural formula, it shows you that hydrogen is single bonded to oxygen, which is then single bonded to another oxygen. So again, it gives you the arrangement of the atoms and shows exactly how that molecule is put together. The halogens, just like hydrogen, will be satisfied with one single bond because there's 7 valence electrons, being 1 short of being a noble gas. They make one covalent bond together, sharing the 1 pair of electrons, giving them each feeling they have 8. And that's why fluorine, chlorine, bromine, and iodine all make diatomic molecules. But unlike hydrogen, they have what we call an unshared pair of electrons. They actually each have 3 unshared pairs of electrons around each atom within their diatomic molecule. These unshared pairs of electrons are also called lone pairs or non-bonded pairs because, again, they're not involved in being shared between those 2 different atoms making a bond. They're just there as extra electrons, again, completing their octet. So we see that here again with fluorine up top, just like chlorine, bromine, and iodine would be, with 7 electrons, 1 short. We see them sharing those 2 electrons in between. Same thing with hydrogen, as we already discussed, sharing those 1 electron each, 2 together, giving them a single covalent bond. Then we see oxygen and nitrogen down below, where one single bond between them isn't enough to complete their octet, but we'll discuss them in a moment. Then here's our structural formula again, where now those shared electrons are being replaced with that dash, and we see 1 dash between fluorine and hydrogen, and then 2 dashes and 3 dashes between oxygen and nitrogen, respectively, because they need to make multiple bonds to complete their octets. And then we do see those lone pairs, unshared pairs, non-bonded pairs, again, around the fluorine, around oxygen, around nitrogen. And if you look at all the electrons involved, again, each dash being 2 electrons, as you see from on the left, again, fluorine has 8 around it on both the left and the right fluorine, because that bond between them does count for both fluorine and for the other fluorine on the right. So like nitrogen and oxygen, as we discussed, they can make multiple bonds between atoms if one bond isn't enough to satisfy their octet. So 2 oxygens coming together, well, 1 bond only gives them 7 in total, so they do need to make a second bond to get to 8. So they can share 2 or 3 pairs of electrons if each atom that is being bonded together has the ability to make another bond. So a double bond, again, is 2 pairs of electrons, like we saw in the oxygen, and a triple bond, therefore, 3 shared pairs of electrons. If, again, the 2 atoms both are still short of the 8 that they have, and they have other electrons that they're able to donate to bond together, then they can make a double or a triple bond together between them. And again, here we see it with the oxygen, again, having 6 valence electrons, needing to get 2 more electrons. Those 2 oxygens can share 2 pairs between them, now giving them 2 lone pairs and 2 bonded pairs, making up their 8 in total. And nitrogen with 5 valence electrons, needing to make 3 pairs of bonds to then get together to make a triple bond between those two nitrogens. Now each nitrogen has one lone pair of electrons and 3 bonded pairs of electrons. Sometimes molecules are formed with what's called a coordinate covalent bond. When a coordinate covalent bond forms, one atom within that molecule shares both of the electrons that go to make a bond together. And though once they are formed, they are exactly the same, they are not any different just in the way in which they come together. They are just as strong. They require just as much energy to break apart. But the way they came together was 2 electrons from one atom, not 1 from each, as we saw in the other examples before. We represent those by showing an arrow, again showing that those 2 electrons did come from that one atom, and it wasn't a 1-to-1 coming together, sharing a pair, that it was 2 from one and 0 from the other coming together to complete that bond. We see a lot in polyatomic ions. When they make their covalent bonds, a lot of times one of the bonds formed is a coordinate covalent bond, because again, one person between those 2 atoms already has a full octet, and another person has 2 short, and so that person with the full octet will donate 2 electrons, make one single bond between them, or make a double bond or a triple bond, sometimes even, to complete the octet of the other atom next to it. One compound that you're probably familiar with that makes a coordinate covalent bond is carbon monoxide. So carbon and oxygen, they come together. Carbon has 4 valence electrons and oxygen has 6 valence electrons. Carbon needs 4 more electrons, but oxygen only needs 2 more electrons. So we see on the left that carbon and oxygen can make a double bond, each contributing 1 electron to each of those bonds, giving now carbon 6 valence electrons and oxygen 8, completing its octet. But oxygen is being complete, leaves carbon short. They can't make another bond giving carbon a now 7th, because that would then give oxygen a 9th. So we see that top pair of electrons there in the middle be donated to make, again, that coordinate covalent bond. So now carbon and oxygen triple bond together, each then having 2 electrons that are not bonded together, and then the other 6 involves in that triple bond between, completing both of their octets. Bond dissociation energy. So when 2 atoms come together and bond, to take those atoms apart from each other, it does require energy. We'll talk about that more when we get to chemical reactions and activation energy. But in any chemical reaction, you have to put some energy in to get the reaction going, because you got to get those atoms apart from each other so that way they can rearrange. So that amount of energy, again, is called the bond dissociation energy. We usually then look at that in terms of per every mole, and a mole is 6.02 times 10 to the 23rd of anything. So we look at a whole mole of the molecule being broken apart, because it's very little bit of energy within one singular molecule or between one bond between 2 atoms. So look at that, again, over a much larger quantity. As you would expect, the larger the amount of energy, therefore the tougher it is to break. So things that are heavier and harder to lift require more energy than things that are lighter. We see that then with also breaking apart these atoms. The more tightly they're bound together, the more energy it takes to rip them apart. The more stable they are when they're bonded together, the more difficult it is to break them apart. Resonance structure. Sometimes when you draw out these Lewis dot structures and you're putting the atoms together to make those molecules, there's actually more than one way in which you can put them together that is perfectly valid, completing everybody's octet, but not the exact same structure when you put it together. So originally what they thought was these electrons that were shared within these molecules would kind of flip back and forth, hence the name resonance, like a bell as it resonates, or a pendulum as it resonates, again going back and forth. But that isn't really the case at all. It actually ends up being a double bond that is shared between actually all 3, and we don't have this actually flipping back and forth, even though it would appear so when you draw out these structures, because you want to put them down, and to show that they are in resonance with each other, you put a double head arrow between them. But again, in reality, they're not really going back and forth. There's just one stable molecule involving all the electrons being shared together, and not actually passing them back and forth and flipping back and forth single and double bonds as originally thought. So here's a molecule that has a resonance structure, ozone. Again, probably one that you're familiar with. O3 is ozone. So on the left, we see one perfectly valid electron dot structure for our ozone, where we have all 3 oxygens having 4 pairs of electrons, 8 valence electrons, having a complete octet. We see the one on the left has 3 lone pairs of electrons with only 1 bonded pair. The one in the middle has 3 bonded pairs with 1 lone pair. And the one on the right has 2 lone pairs and 2 bonded pairs. Again, giving them all 4 pairs, giving them 8 valence electrons. But on the right, we see the oxygen on the left this time now has a double bond with only 2 lone pairs. The one in the middle still has 3 pairs of electrons that are shared, 1 non-shared pair of electrons, again giving it 8. And then the one on the right having the 3 lone pairs of electrons, 1 bonded pair of electrons, giving it its 8. So again, we show those with that double-headed arrow between those 2 perfectly acceptable Lewis dot structures, completing everybody's octet, but they are certainly not the same. That being said, there are times when you cannot complete an octet, and we see that with nitrogen dioxide. So 1 nitrogen with 2 oxygens, nitrogen having 5 valence electrons, oxygen having 6 valence electrons, 2 of them making 12 plus that 5 gives you 17. There's no way you can make pairs of electrons out of an odd amount. So that was on the screen prior. Again, there were 4 different pairs, whether they were bonded pairs or lone pairs. You still have 4 pairs of electrons for each atom, giving them the 8, completing their octet. But when you have 17, you can't get pairs out of an odd amount. So nitrogen dioxide cannot complete its octet, and that's just the way it goes. Then other times we see, like boron, BF3, boron trifluoride, where boron has 3 valence electrons. It'll make 3 bonds with a fluorine, giving each of those fluorines then their 8, and boron now only has 6, and that is complete as boron can get. So boron remains with just its 6 valence electrons. It makes it more stable having those 6 than the 3 they had before, but it cannot complete its octet. And then oppositely, we can see here PCl5, phosphorus pentachloride, where it's going to have what we call an expanded octet, because that phosphorus has 5 valence electrons. It's going to bond with each one of its 5 valence electrons with another chlorine, giving it now actually 10 valence electrons, going beyond that octet.